Ratios and proportionality. First we'll learn how to work with ratios. So first and foremost, what is a ratio? A ratio is a relationship between two quantities that have the same units. For example, this could be two lengths or two weights, or masses in other words, in units of kg or pounds if you're American, or this could be two heights. And since a ratio is a fraction of two quantities with the same units, the units cancel out, and therefore the ratio itself is actually unitless. Let's look at an example. For a rectangle with a width of 10 meters and a length of 30 meters, what is the ratio of length to width? So this is the rectangle in question with a width of 10 meters and a length of 30 meters. Then we need to find the ratio of length to width. So we would simply just say length of 30 meters divided by width of 10 meters, giving the ratio as 3. Then for another example, for a rectangle with a length of 25 centimeters and a width of 1 meter, what is the ratio of length to width? So this is very similar to the previous example where we would first just say ratio is equal to length divided by width. Then the only thing that's new is this time the units are different. So the question is, will the ratio just be the length of 25 centimeters divided by the width of 1 meter? No, that's incorrect. You first have to make them both into the same units so that the units can cancel out. Otherwise, if you're to determine this, you get a value of 25 centimeters per meter. Even though they both represent lengths, they're still not the exact same units. So we need to make them both into the same unit. So we can do that either by making the 25 centimeters into meters or by making the 1 meter into centimeters. I'll go with changing the 1 meter to centimeters. There, now they have the same units. And then we'll just do the same calculation as before, which would give a value of 1/4. So another thing to keep in mind is it wouldn't just stay as 25/100. With ratios, you need to turn it into the most simplified fraction that it can become. So 25/100 turns to 1/4. And that's the ratio representing the length to the width. And whenever working with the ratios, make sure to leave it as a fraction. So don't change it into a decimal. So you wouldn't change this to 0.25. Leave it as 1/4. So that's the basic idea of a ratio. And then ratios are useful because they give a good comparison between two numbers. However, they don't say anything about the actual values. So to understand this, we can just look at this ratio we just determined of 1/4. If you're just told that the ratio of the length to the width is 1/4, and then you are asked, what is the length? Unless you're given the width already with units, you wouldn't be able to determine what the actual length is just from the value of the ratio. And for example, we can look at another bunch of values, both a ratio of 10 centimeter length to 20 centimeter width and a ratio of 25 meter length to 50 meter width will give a length to width ratio of 1/2. So while a ratio can be a useful piece of information, it's not the full picture. And that's everything you need to know about ratios. We can now look at proportionality. So you've probably seen the word proportion a bunch of times before, but what does it exactly mean? Proportion just refers to the equality of ratios. For example, the ratio 10/20 is equal to the ratio of 25/50. Since both of these will just simplify down to 1/2. Therefore, since the ratios are equal to each other, we can say that they're in proportion, or the two ratios are proportional. And once we know two ratios are proportional to each other, we can play around with them a bit. So taking this example of 10/20 and 25/50, we can cross multiply the two fractions and they'll still stay true. So for example, 10 times 50 is equal to 25 times 20, since both of these would give a value of 500. Or if we want, we can invert the two fractions changing them to 20 over 10 is equal to 50 over 25, both of which would just simplify down to 2 over 1. So it's nothing so fancy. It's just once we know two ratios are equal, we're allowed to apply basic maths rules to them. And you can use this in a bunch of ways. Let's apply to the lengths of two lines, for example. So we have line 1 and line 2, and we're told that line 1 and line 2 are in proportion. From that, we can derive a bunch of information and equate a bunch of ratios. So for one, we can say that A over B is equal to E over F. So that's the ratio of the smaller side to the longer side is equal for both lines. Then we can also find ratios of lengths across the two lines. We could say the length of the smaller side on line 1 over the length of the smaller side on line 2 is equal to the length of the longer side on line 1 over the length of the longer side on line 2. And the reason this works is because basically, since the two lines are in proportion, it just means that you get line 2 when you multiply line 1 by a certain number. Therefore, A over E and B over F will both represent 1 over this number. Then another interesting ratio we can get is by equating the fraction of the smaller side over the total length of the line. So for line 1, that would be A over A plus B. And that would be equal to the same ratio on the second line, meaning shorter side E over total length E plus F. So it may seem a bit abstract now since we're just working with letters. So let me replace these with some numbers. There we go. So I made the shorter part a length of 1. We don't need to worry about the units. And the longer portion, length of 3 for line 1, and for line 2, shorter portion has length 2 and longer portion has length 6. So applying those exact same ratios, these ones, we would get A over B equals to E over F, or in other words, 1 over 3 is equal to 2 over 6. And that means for both lines, the shorter portion is 1/3 of the longer portion, since this 2 over 6 would also simplify to 1 over 3. Then the next was comparing the relative lengths on one line to that on the other, which gave 1 over 2 is equal to 3 over 6. And that implies that the first line is half the length of the second line. And then finally, for this ratio, meaning what fraction of the total line length is occupied by the shorter portion. So for the first line, that would be 1 over 1 plus 3, and this would be equal to the case for the second line, which is 2 over 2 plus 6, which in both cases would give 1 over 4. Therefore, the shorter portion is 1/4 the total length of the line in both cases, since they're proportional. Let's look at another example. A box of 70 balls has black, blue, and orange balls in a ratio of 1:3:3 respectively. How many balls of each color are in the box? So the first thing to do is we need to rewrite this ratio in a more usable form, meaning in the form of a fraction. And how you do that is by saying the number you're focusing on divided by the sum of all these numbers. So first, for the black balls, that would be 1 over 1 plus 3 plus 3, which gives the ratio 1 over 7. For the blue balls, it would be the second number, meaning 3 divided by 1 plus 3 plus 3, giving its ratio as 3 over 7. And lastly, for the orange balls, their number is also 3. So their ratio, like the blue balls, would also be 3 over 7. And now that we have the ratios in this workable form, we just need to multiply them separately by the total number of balls to determine how many balls there are in each color. So first, for the black balls, this would be 1 over 7 times total, which is 70, which gives the number of black balls as 10. Then the number of blue balls would be 3 over 7 times 70, giving a value of 30 blue balls. And lastly, the orange balls would also be 3 over 7 times 70, therefore there would also be 30 orange balls. And once you've worked out to this point, in case you're still not sure whether you worked it out correctly, a nice little trick you can use to check this is just add up the number of balls and see if they give you the correct number as stated in the question. So 10 plus 30 plus 30 would indeed give you a value of 70. Therefore, we know it's correct. Then here's another example. Here we have to solve for x. So we have two ratios that are proportional to each other. Then it's just simple rearranging to solve for x. So for part A, we have x over 27 is equal to 51 over 81. So to solve for x, you just take the 27 to the other side and say 51 over 81 times 27. And that gives a value of 17. Then for part B, we have negative 2 over x minus 7 is equal to x plus 1 over 8. So this time it's not going to be as simple to solve for x, but the first step would be cross multiply. You'd say x minus 7 times x plus 1 is equal to negative 2 times 8, which gives a value of negative 16. And you just multiply out the brackets and simplify, giving it as x squared minus 6x minus 7 is equal to negative 16, and take the negative 16 to this side, which gives x squared minus 6x plus 9 is equal to 0. And thankfully this would be pretty simple to factorize, and it will just come down to x minus 3 times x minus 3. In other words, x minus 3 squared is equal to 0. Then we just equate the two and we have x minus 3 is equal to 0, therefore giving the value of x as 3. And again, you can just verify the answer by substituting it back into this statement, which would be negative 2 over 3 minus 7, meaning negative 2 over negative 4, which gives a value of half, is equal to 3 plus 1, which is 4 over 8, which also gives a ratio of half. So we know it's correct. Then here's a final example, just for practice on working with ratios in proportionality. In the question, we have line xy, which is 20 meters in length. Then we're told that the point O divides line xy in the ratio of 2 to 3. And the question asks us to determine the lengths of OX and OY. So the first part of solving such a question is you need to correctly interpret the information given in the question. So we have the line xy, and we're told the point O divides the line xy in the ratio of 2 to 3. That means we'll need to draw a point O somewhere along this line to split the line into this ratio. And that could be achieved in the following manner. Here's the line xy, then I put the point O here so that it divides the line xy into a portion made up of 2 lines and a portion made up of 3 lines. So luckily I set it up so it corresponds with the number of lines, just so it's convenient for you to see as well. But I guess in your situation in a test or exam, you wouldn't have these lines. It'll just be printed on a plain white paper. So you just need to realize that it's split into unequal portions, the first being slightly shorter than the second. And also the way it's worded is important because it says it divides the line x, y in the ratio of 2:3. So since it started with x, it means the first number in the ratio would correspond to xo, and the second number would correspond to oy. If instead they had said something like the point O divides the line yx in the ratio of 2:3, then it would be a slightly different story where we would look at it starting from the y end, and then we would have 2 lines here, the point, and then there would be 3 lines. But luckily that's not the case, and they mentioned the line xy. So I just brought attention to that just so you realize the funny tricks it can pull on you and where you can lose marks. So anyway, coming back to the question, they asked us to determine the lengths OX and OY. So OX would be this length, which is the same as XO. And then the first step is we need to convert this ratio into a workable form, meaning into fractions. So for OX or XO, that would be XO over XY is equal to 2 over 2 plus 3, giving the ratio as 2 over 5, which is the same as OX over XY. Then to get the length OX, we'll just say this is a ratio of OX over XY times length of XY, which is 20 meters. And that gives the length of OX as 8 meters. And don't forget to include the units. Then similarly for OY, we get the length of OY as 12 meters. And with that, you should hopefully have a pretty comfortable understanding of ratios and proportionality. And based on that assumption, I'll move on to something a little more complex, and that is proportionality of triangles. Under proportionality of triangles, we'll look at how the areas of different triangles can be related to each other relative to their respective heights and bases. And there's two particular situations to know about. The first is the case where you have two triangles with the same height but different bases. And as you already know, the area of a triangle is calculated by saying half of base times height. But something you may not know is that the height just refers to the perpendicular distance from the base to the top vertex. So even when that height is not part of the actual triangle, such as in this case where the region with this height isn't actually part of the triangle, the formula still applies. So the area is just determined by saying half of the base, whatever it is, times the perpendicular height, which is something which may not be so evident when you see it applied to just a regular triangle with a clear height indicated in it. So a conclusion that can be drawn based on this is that the area of triangles with the same height is proportional to their bases. And this can be shown mathematically by taking the ratio of the areas for these two triangles, meaning the area of triangle ABC divided by the area of triangle DEF. And you determine the area for both by saying half of base times height. Then replacing these terms with the sides that would actually represent them gives half times AC times H for ABC, meaning half times this base AC times the height. And for DEF, it would be half times the base of DF times the same height as for triangle ABC, since both triangles lie between parallel lines. Therefore, the perpendicular height is the same. Then in this fraction, the halves would cancel out and the h's would cancel out, leaving just the ratio of the two bases. Therefore, triangles with the same height have areas proportional to their bases. Then the other case that's relevant is the area for two triangles that have the same base and the same height. And this diagram depicts an example of such a case where both triangle ADC and triangle ABC have a base of AC and both have a perpendicular height of H. And the implication of this is that triangles with the same height and the same base have equal areas. And this can be demonstrated by finding the ratio of their areas. So I took area of triangle ABC divided by area of triangle ADC, which would be half base times height for both. Then replace the bases with the terms that would actually represent them in the diagram, which is AC for both triangles. And therefore, all the terms in the denominator and the numerator will cancel off, leaving a ratio of 1 over 1. Therefore, the area of ABC will be equal to the area of ADC. So that's the, I guess, mathematical justification for why these two triangles have the same area. But just by looking at them, you can tell that, well, yeah, they do look like they probably have similar areas because they both have this section and then these two sections are not that different. But you can't tell just by looking that these two have the exact same area. So I'll give a visual justification as well, just to solidify the idea in your mind and fully convince you. And to do this, I need ABC to be an equilateral triangle. So here we go. Here we have ABC as an equilateral triangle. Then what I did was I set up the line DC so that it cuts the line AB in half. And that's useful because this line cuts this triangle into half, meaning the area of ABC is this total, meaning double of this area, and then the area of ADC is this area times 2, since this region is the same as this region. So essentially, both ABC and ADC involve just a doubling of this area to determine the total area. Therefore, both triangles will have exactly the same area. I hope that convinces you that the areas for two triangles with the same base and the same height are actually the same. Let's go through an example.